Thank you for the introduction. Thank you for knowing what ASI stands for.
I don't think
Okay. Yeah, now I don't have to say it out loud ever. So I'll start by introducing the setting for the well-known Lovasz Local Lemma. So this will start with a definition of a fairly general way to give a combinatorial problem. So a CSP, which stands for constraint satisfaction problem, is a triple X, K, B, where X is a set, K is a natural number, and B is a set of what we call constraints. So these are pairs, let's say S little b, or not curly b, where S is a non-empty finite subset of X, and B is some set of functions from this domain S into K. And we think of this as sort of bad configurations on the set S. And that'll make more sense once I say something in a bit. But also, since you can sort of recover S from B, I'll just identify this with the set B, and I'll call S the domain of B. And similarly, since you can essentially infer X and K from B, I'll just identify this with B. So a solution to such a thing is a labeling of all the elements of X so that all of these bad configurations are avoided. So it's a function f from X to K such that for all B and B, so for all constraints, if I look at f on the domain of that constraint, it's not one of my disallowed configurations. And of course, we're going to care about doing combinatorics in a Borel or measurable, etc. setting. So a Borel, measurable, etc. CSP is a triple where like this, but now X is a standard Borel space or standard probability space and so on. And B is Borel in the appropriate space of finite things. And then, of course, a solution will be Borel or measurable and so on if it is as a function. Is anything unclear about the setup of a CSP?
Yeah, just I don't see the S anymore on the right. Is that not?
Yeah, so
Domain of B.
I like to say it like this because I like to think about it as a pair, but I can always just refer to S by B. So I call it the domain of B.
Okay,
I guess I should have just done it the more normal way. But yeah, there we go.
thank you.
Right. So the Lovasz Local Lemma is a famous tool from finite combinatorics that lets us build solutions to CSPs sort of randomly. So to state it, we need a few more parameters associated to the graph, or associated to the CSP. So for B, a constraint, D of B will denote the number of constraints that B interacts with in the sense that their domains overlap. So it's the number of B prime in script B, so that domain B intersect domain B prime is non-empty. So when we're assigning, if we're trying to randomly build a solution, DB is going to tell us like how many other events we need to worry about B interacting with. If there's a lot of independence, that makes our job easier generally. And then PB is just going to be the probability that we fail at B if we just do things completely randomly. So we can just compute this as the size of B over K to the domain size of the domain of B. But the point is that this is the probability a failure, i.e. that f is in B for f chosen uniformly at random in the set of functions from domain of B to K. So the idea is that if both of these are small everywhere, then we're going to have an easy time. So P, which if there's more than one CSP to consider, I'll write as P of the entire CSP curly B, is just going to be the supremum over all B of P of B, and likewise for D, which we'll call D of curly B if necessary. And let's assume for this talk that this D is always finite. So one more thing that you don't need for the statement of the local lemma, but which will be important for this talk, is a graph that I can associate to the CSP. So let G sub B be the graph on X given by X, Y are adjacent if they share in some constraint. So if there exists a constraint B, so that X and Y are both in the domain of B. And I guess also X does not equal Y. And notice that this is Borel if B is, and this technical condition that each point X is in countably many constraints. And actually for this whole talk, I'll assume without mentioning it again that each point is always going to be infinitely many constraints. So assume. So now we can state the lemma, which I'll call a theorem. So this is the Lovasz Local Lemma, or at least a popular version of it. There's a more general thing you can say. So it says that if these probabilities and these degrees aren't too high, I can find a solution. So if EPD, this is just the number 7 something, is at most 1, then my CSP just has some solution classically. And this is very useful for solving all sorts of problems in finite combinatorics. But we want to do things in measurable combinatorics. Luckily for us, there are many known versions of this local lemma in the Borel or measurable setting. So I'll list some of these known results now. So Bernshteyn showed that if B is Borel and mu is a Borel probability measure on X, so I'll fix the meaning of X and K and B for the rest of the talk. And I have a stronger inequality that where E is replaced with 2 to the 15 and D is replaced with D to the 8th, then B admits a mu measurable solution. And just to pretend that we're doing measured group theory, I'll add that he showed separately that if this graph GB is a Bernoulli shift and B satisfies some invariance condition, which I won't define, then the original inequality suffices. But now we need to sort of break with tradition a little bit, because this talk is really most interesting if we're not throwing away null sets all the time. So there are some versions of this of these descriptive local lemmas where you don't lose anything, and there are also some where you lose meager sets, which are also interesting to me. So first I'll mention, this is still Bernshteyn, that if B is Borel and X now has some Polish structure, and again you have this inequality with the D to the 8th, and B has a bare measurable solution. So there are also versions where you don't lose anything, but in these you do have to weaken, or I guess strengthen your assumptions significantly. So you lose a lot of strength. So the first one I'll mention is due to Csoka, Grabowski, Mate, Kukurko, and Tyros, is that if you have a geometric constraint on GB, that it's sub-exponential growth, GB is sub-exponential growth, and you have this original inequality, then B has a fully Borel solution. The next one I'll mention is that if you don't want any geometric constraints on the problem, then you need a significantly better inequality. So I'll attribute this to Brandt, Brunau, and Rojon. If B is Borel, and I replace my inequality with one that's exponential in D, so P times 2 to the D is less than 1, then B has a Borel solution. So these authors were actually working in a field called distributed computing, but by some work of Anton that links distributed computing and Borel combinatorics, this follows immediately from what they showed. And I'll mention a question that I find interesting. So in this result and this result, does the original inequality EPD less than or equal 1 suffice? Any questions? Okay, now I can talk about the other part of the title, ASI, which stands for asymptotic separation index. So this is a geometric notion related to toast, but also related to hyperfiniteness, and it's kind of aesthetically similar to Gromov's notion of asymptotic dimension. So let G be any Borel graph. So we say that the ASI of G is at most S, where S is some natural number. If for all natural numbers R, we think of this as like a scale, there exists a Borel partition of the vertex set into S plus 1 many sets. So by this, I just mean each set is Borel. US, such that, and I'll explain this, G to the less than or equal R restricted to mu I is going to be a component finite graph. So this is the distance R graph, by which I mean the graph that extends G by connecting 2 points if their path distance is at most R. So this is saying, even if I zoom out at a large scale, I can separate G in a Borel way into this many component finite subgraphs that are, yeah. ASI has turned out to be a both combinatorially useful, as we'll see later, and maybe surprisingly common condition in Borel combinatorics. So this set of theorems will show you the common part. So these are a mix of work due to Conley, Jackson, Mark Seward, Tucker Drob, who are also responsible, by the way, for the notion of ASI, and to Conley and Miller. So let G be a locally finite Borel graph. So first of all, automatically, there exists a Borel G invariant co-meager set C, such that if I restrict G to this large set, it has ASI at most 1. Second, if mu is a Borel probability measure on the vertices, and G is hyperfinite for this measure, G is mu hyperfinite, the same holds with co-null in place of co-meager. And most interesting for this talk is going to be the following class of examples. So a Schreier graph, no, that's not right, of a free Borel action of any of the following has ASI at most one. I guess exactly. So this is a non-exhaustive list, but I'll just mention some that I'd like to emphasize. So the first is the Lamplighter group Z mod 2 Wreath Z. The second is the Baumslag Solitar group 1, 2. And the third is any polycyclic group. Yeah, and more. The general condition here is that this is just going to be groups whose Borel asymptotic dimension is finite, and they provided a very general and hard to state condition that all of these groups meet. But I want to emphasize these ones. These are nice examples with exponential growth, which is exciting for us, as we're about to see. I'll also mention an interesting open question that sort of motivates me, at least, to think about ASI, is that we don't know if there are Borel graphs G with the ASI of G strictly larger than 1, but still finite. Any questions about ASI? So now we're going to see the useful part by stating a Borel local lemma for graphs with finite ASI. So this is the main theorem of my work with Bernshteyn. So let B be a Borel CSP with ASI of the associated graph being some finite number S. If I have the inequality P times ED to the S plus 1 is at most 1, there is a solution, a Borel solution to B. So I'll say more about some consequences at the end, but the one I want to emphasize the most right off the bat is that because of examples like these ones, this is the first sort of somewhat generally applicable Borel local lemma with a polynomial inequality that can apply to exponential growth groups. And that's also like the source of my claim that this is a talk about measured group theory. Okay. The proof is actually very simple. It uses an idea that's common in the literature around the local lemma, which is just to sort of build a solution a little bit at a time and keep track of the conditional probability at each step that you're going to fail at the end.
You have this nice picture of ASI that you drew once, I think, in like maybe University of Florida or something. Maybe that would be helpful. It was helpful for me.
Yeah, the disappointing thing about the picture is that it's going to look like toast. And you can actually prove that it has to if you do it on a plane. So that's the issue here. But you draw a toast, as one does.
There are colors too, like on the paper.
Yes. And you sort of thicken up the boundaries of your toast depending on what scale R you want. So the union of all these thickened boundaries will be one of your component finite sets, and everything else will be the other one. So this is what ASI 1 looks like in the plane, at least.
You mean there are two? Is the ASI 1?
Yes, I'll use another color.
Thank you.
Yes, no problem. It was a good suggestion. I am really running out of long chalk. Okay, so I guess the proof will be moved over here. I think also the sort of simplicity of this proof indicates that when you apply this, most of the work will have been done by this set of results. Proving ASI 1 is a lot harder than using it. Right, so prove by induction on S that it suffices to witness ASI S using the scale R equals 1, actually. This weird comment will be important for the induction actually being valid. So S equals 0 is the usual Lovasz Local Lemma. Right, because here the components are just finite. And we sort of saw last week how when your graph is component finite, you can, in a Borel way, using some uniformization theorem, just pick solutions on each component if they exist. And also when S equals 0, this becomes the usual inequality, PED is less than or equal to 1. Okay, so for the inductive step, suppose I have this with each UI Borel and GB restricted to UI component finite. We're going to split B into two Borel CSPs, B0 and B1. Each constraint B, so here's the domain of B, will be split exactly into two constraints in these two CSPs, where the domain of B0, oh yeah, I wanted to say, let W be everything except this U0. And the point is that W satisfies, the sets U1 through US witness ASI at most S minus 1 for the scale R equals 1 for the set W. So that's how the induction will go. So the domain of B0 is just going to be whatever was in the domain of B and U0, and the domain of B1 is just going to be everything else, so from W. Right, so here's our original constraint. These sets U0 and W split everything in half. So on here we get a constraint B0, and on here we get a constraint B1. So I have to say, what are the bad events for these constraints? Well, a bad event for B0 is just that whatever you assign there makes the conditional probability of violating this constraint, once I fill in the rest of this original constraint, higher than is good. So I'll say F is going to actually be bad according to B0 if this probability that a G chosen at random on the whole of B is in B, given that G agrees with F on U0 is large. So ED to the minus S will work. So applying Markov's inequality tells you that since the original probability of violating B was at most ED to the negative S plus 1, that the bad probability for this new thing B0 is going to be at most 1 over ED. Hey, we're just going to roll with it. So also, well, yeah, so by the usual local lemma, I'll also mention that the D's are never going up because of how I picked my constraints. So the D's are just at most whatever the original D was. So by the usual Lovasz local lemma, B0 has a solution. And because the associated graph is component finite.
The intersection degree of the domains?
Yes. So the domains just got smaller.
Yeah.
So because this U0 is component finite, it's going to have a Borel solution. So you induction purists out there will notice that I probably should have started at S equals -1, but I thought that would be confusing, so I just repeat myself a little. But it does bother me too, don't worry. Okay, so call it F. And now, of course, I won't write it out, but I'll just say define B1 exactly so that G from W to K is a solution to B1 if and only if G disjoint union this F that we already set is a solution to B. So this makes it clear how to actually define it. And the point is that B0 was exactly set up so that F being a solution means the probability of failure for B1 is at most ED to the minus S. So now we apply our inductive hypothesis to say that B1 has a Borel solution G. Right. I guess I don't have time to talk about applications. Okay. So there's a very rich world that connects this stuff and distributed computing and Borel combinatorics that would be great to talk about. But I'll just mention that's a little bit more involved. So the one consequence I'll mention, besides local lemma for exponential growth graphs, is one other short consequence. This relates to a question I stated earlier. So the bare measurable Lovasz Local Lemma only needs E squared P D squared at most 1. So it improves the octic to a quadratic. Admittedly, in practice, usually all the polynomial inequalities are going to function about the same way, although there are some cases where the difference matters. But I think the more interesting thing here is just this academic question of whether or not EPD suffices. So I'll stop there.
Mention one application, like more.
Yeah, sure. So this is actually the original reason we started talking about this. So I don't have time to explain how, like, what a local algorithm is or how it relates. But one corollary of this is that Borel-Brooks theorem holds for graphs G with finite ASI. And the proof is that there is a known fast randomized for Brooks theorem. This is the theorem that you can delta color a max degree delta graph if it doesn't have any delta plus 1 clicks.
And you use your Lovasz Local Lemma to do the translation from the distributed computing to here.
Yeah, so that part's all very standard. So in general, this machinery that was originally built up by Anton applies just as well here. So it says that, for example, if you have a little o log n random distributed algorithm for solving a problem, then you can always solve that problem in a Borel way on finite ASI graph.
But then where do you use your local lemma?
Well, because this translation uses the descriptive local lemma. Yes.
Other questions? Let's have Felix again.